is problem set number 5, problem 2. 2-point charges Q1, which is equal to 3 microcoulombs, and Q2, which is equal to 2 microcoulombs, are attached to the floor as drawn. Point A is located a distance of d1 equals 1 times 10 to the minus 3 meters to the right of Q1, and d2, which is 1.5 times 10 to the minus 3 meters above Q2. Point A is not a charge, it is just a spot on the floor. Part A, suppose we place a particle of charge capital Q equals 0.01 microcoulombs on the floor at point A. What is the magnitude of the force felt by capital Q? In what direction, part B, in what direction does that force push Q, capital Q? And express your answer as an angle above the horizontal. Part C, where could we place capital Q so that it would feel no electric force? Be as specific as possible, but use your intuition to get started. How far from Q1 should we put capital Q? Set up but do not solve the relevant equation unless you need the algebra practice. Okay. So let's write down our givens. We know that Q1 is equal to 3 microcoulombs, or 3 times 10 to the minus 6 coulombs. Q2 is equal to 2 times 10 to the minus 6 coulombs. D1 is equal to 1 times 10 to the minus 3 meters. D2 is equal to 1.5 times 10 to the minus 3 meters. Okay. And something that you should have in your cheat sheet is that K, the value for K, the electrostatic constant, which is found in the Coulomb's law, its value is 9 times 10 to the 9 Newton meter squared per Coulomb. Okay? So that is the value of K. All right, so part A. What is the magnitude of force felt by particle Q? And I'm just going to encircle particle Q here. It will take, so a particle of charge capital Q of 0.01 times 10 to the negative 6 coulombs is going to be felt, or is going to be placed right here. Okay, so that will be Q equals 0.01 times 10 to the minus 6 coulombs. This spot right here. All right. So I guess that's given. If Q equals 0.01 times 10 to the minus 6 coulombs, located at point A, find the magnitude of force felt by Q. Okay. So, according to Coulomb's law, the formula for electrostatic force, right, that's going to be equal to K times the magnitude of the charge 1 times the magnitude of charge 2 divided by r squared. So let me just clarify some things. That's a constant. This is the electrostatic constant, so that never changes. Okay? Q1 right here is going to be one of the charges. So we solve it for one at a time. We have force due to Q1 and force due to Q2, right? So we're not going to combine that right away. First, I want to know what the charge is from Q1. And so I'll plug that in Q1 right here. And this Q2 that you see here won't be this Q2. This Q2 is going to be the charge of our point right here. So that is Q1 is this guy Q2 will be this guy for force 1, okay? Just want to clarify that. And for force 2, Q1 will be this force, or whatever point charge we have in the floor. And then Q2 will be the particle that we added that we want to find out the force, the electrostatic force felt by that part. Okay, so that is Q2. Okay, so let's write that down, okay? So I guess I'll draw. Let's make a visual right here. So we have our coordinate system of x and y, right? Right here. So this is, oops. This is y and this is x. And I have this particle of charge, capital Q, that we placed right here, right? That's this guy, okay? So we see that we're going to feel some sort of force from Q1 due to Q1 coming this way, right? Q1 will push it this way. Because they're both positive charges. So that will be force 1. And Q2 right here will push it going upwards or towards positive y, right? So that will be F2. So let's draw that in our coordinate system. Okay, so here I have F1, or force due to Q1, and here I have F2, which is my force due to Q2. Okay? So let's do that. So my magnitude of force due to Q1 is equal to K times the magnitude of Q1 times, remember, this guy is always the particle of charge Q that we want to know the force felt by Q, right? So that's always this capital Q right there. Okay, so times capital, times the magnitude of capital Q divided by R2, which for force number 1, the distance between the center of charges of Q1 and capital Q is D1, right here highlighted. And the value of that is D1 is 1 times 10 to the minus 3 meters. Or actually, I'll write that as D1 for now. So that will be D1 squared. Okay? So let's plug that in. That's K, which is 9 times 10 to the 9 Newton meter squared per coulomb, times Q1, which is 3 times 10 to the minus 6 coulombs, times capital Q, which has a charge of 0.01 times 10 to the minus 6 coulombs. And we divide that by D1, which is 1 times 10 to the minus 3 meters. All right. Plug that in your calculator. You will get that the magnitude of force due to Q1 felt on capital Q is equal to 0.27 newtons. Okay. And the force due to Q2 that is felt on capital Q is going to be equal to K. And this time the source charge is not Q1, but this time the source charge is Q2, right? So I'm not going to put Q2 down. That's why it's important to understand this equation. You can't just plug in Q1 or Q2. You have to understand, what does Q1 mean here? This is a source charge. So initially, our source charge for F1 was Q1, but now for F2, our source charge is now Q2, okay? Okay, so this is a source charge, and then this is going to be the charge. This here is going to be the charge of Q, of capital Q. The point that we add, the particle of charge that we add. So now, again, the electrostatic force is K times Q2, that's a source charge, times capital Q, or the particle of charge we added, divided by, now the distance between the center of charges is going to be different, right? Because the force due to Q2 is going to be d2 distance away from capital Q. So this will be divided by d2 squared. And if you just fill that in, that will be 9 times 10 Newton meters squared per coulomb times Q2, which is 2 times 10 to the minus 6 coulombs. And the charge for capital Q, which is 0.01 times 10 to the minus 6 coulombs. And that's divided by D2, which is 1.50 times 10 to the minus 3 meters, right? So if you plug that in the calculator, the magnitude for force due to Q2 is equal to 0.12 newtons. Okay, so now let's get F total, right? Which is what we wanted to find. We wanted to find the magnitude of the force felt by Q, which is going to be the summation of the sum of force 2 and force 1 felt on Q. So if, in order to do that, here, right, looking at this free body diagram there, if we look at the two forces, we have force 2, F2, which we calculated, and F1 going towards the x direction, which we also calculated, right? Or actually, I will rewrite this as F1 is going this way, F2 is going that way, up, right? And this is 90 degrees. We'll have a total F going this way, F total, which is just going to be the hypotenuse of this right triangle, right? And that will equal to the square root of F1 squared plus F2 squared, right? So let's calculate the magnitude of force felt on Q. So F total magnitude is equal to the square root of force due to force 1 squared plus the force magnitude of force due to Q2 squared. Okay, so that is equal to the square root of 0.27 newtons squared plus the force 2, which is 0.12 newtons squared. Okay. And if you plug that in your calculator, you would find that the total force is equal to 0.00105 newtons. And that is our answer for part A. All right. For part B, the question is, in what direction does that force that we calculated, the total force, magnitude of force felt by Q, in what direction does that force push Q towards? And express your answer as an angle above the horizontal. So basically what we want now is, I'll use pink. Now what we want is the angle, this guy, above horizontal, which we can do easily, right? Because we have all the value for all the sides, F1, F2, and F total. We can now find theta. So for part B, part B, what is theta? Well, we can use the value of F1 and F2 to find theta, right? So let's say, I'm sure you guys probably know this already. SOHCAHTOA. I haven't been in school for almost 3 years and I still cannot forget this word, so I'm sure you guys also know this pretty well. Anyways, we're going to use this SOHCAHTOA to find our theta. So let's say the tangent of theta, that's the opposite of theta, which is F2, over adjacent, which is F1, right? So that means that theta is equal to inverse tangent of F2 over F1. Which is equal to inverse tangent of F2, which is 0.12 newtons, and F1, which is 0.27 newtons. All right, the units will cancel out, and I would get that theta is equal to 23.96 degrees above the horizontal. Okay. And now moving on to part C. Where could we place capital Q so that it would feel no electric force? Be as specific as possible, but use your intuition to get started. How far from Q1 should we put capital Q? Okay. In order for capital Q to feel no force, so now we're moving on to part C. I imagine it would have to be somewhere between a straight line of Q1 and Q2, right? So let's say we have, I'll use blue for the, no, I will use brown for the Q. So let's say I have Q1 right here, right? And I draw a straight line, and I have Q2 right here. Okay, and the angle of this line is 180 degrees. So it's a perfectly straight line. Because it's a perfectly straight line, and let's say I have my coordinate system of X and Y, I know that if I place point Q somewhere here, that it's not going to have a force in the Y component, right? Because everything's going to be pushing. Everything is going to be pushing horizontally. So there's going to be a force F1 here, and the force F2 this way. But it won't feel any forces along the y direction, right? So it's just a x component of forces. And if the charge of Q1 was equal to the charge of Q2, then I would place point Q directly in the middle of this line, because then the charges or the forces F1 would be opposite and equal to F2. So they would cancel out, right? But in this problem, that's not the case. In this problem, the forces are not, or the charge of Q1 is not equal to the charge of Q2, right? I believe the charge of Q1 was equal to 3 times 10 to the minus 6 coulombs, and Q2 was 2 times 10 to the minus 6 coulombs. So just with my intuition, I would think that the force due to Q1 would be greater since it has a larger charge. So likely I would have to be farther away from Q1 than Q2 and closer to Q2. That's just my intuition. I don't know if that's true or not. That's what we're going to find out. Okay? So I will call the distance between Q1 and Q2. I'm going to call this length L. Okay, distance L. And whatever this distance is, remember, I did not put Q in the middle, right? I just put it at some random distance, let's call it X, okay? So in order for particle Q to feel no force, I'm going to place it in a straight line between Q1 and Q2. I know that. It needs to be there because I can't have a y component. I'm trying to cancel out x components right now of force. Okay? So my summation of forces along x is going to be equal to F1, which is pointing towards positive x, minus F2, which is pointing towards negative x. And that's going to equal 0. All right, so in other words, F1 would be equal to F2. Okay? And again, what is force? Force is K, or the electrostatic constant, times Q1 from the source charge, times capital Q, which is the charge of our particle, divided by the distance. The distance from Q1 to Q is x right here, right? So this is going to be x squared, and that is equal to the electrostatic constant, K, times, what is our source charge for F2? Source charge is Q2, and what is the particle charge that we're looking for? That's capital Q, divided by the distance between the center of charges. So the distance between Q and capital Q and Q2 right here, it's going to be this, which is L minus X, right? Okay, so times L minus X squared. Okay, so right away I'm just going to go ahead and cancel out. I'm going to divide both sides by K and capital Q, since they both have that. And so I'm going to be left with Q1 divided by x squared is equal to Q2 divided by L minus X squared. Okay? And because these two fractions are equivalent, I could rewrite this, right? I could call this L minus X squared divided by x squared is equal to q2 over q1, right? So I'm going to take the square root of both sides of the equation, right? Take square root of both sides of the equation. So if I do that, I would get L minus x is over x is equal to the square root of q2 over q1, right? And I'm gonna rewrite L minus x over x as L over x minus x over x, which is just 1, is gonna be equal to the square root of q2 over q1. All right? And so now I'll just solve for x. So L over x is gonna be equal to 1 plus square root of q2 over q1. So therefore x will be equal to L over 1 plus the square root of q2 over q1. All right, so that would be my distance between q1 and q in order for q to feel no force. Okay. So, yeah, hope that was fairly clear.